set is one that consists entirely of interior points. Now, you've seen before open intervals. If you have an open interval, you have the two boundaries, A and B, and an open interval. The endpoints were not included. So any number I pick, I can draw a circle around it, kind of. There's another, like, open interval within it that's going to be entirely in that interval itself. So if I pick a point, though, that is on the boundary over here, like B, I cannot put an open interval over it, because that will be half inside, half outside. Okay, so our definition for an open interval is going to be an open set. I mean, an open set consists entirely of interior points. And a closed set, well, a closed set now consists of the interior and the boundary. Consists of the interior closed set consists of the boundary points. It may also include the interior. So, but what I'm trying to say is that it does not have to include the interior. If I have that interval here where I had my interval AB, the set AB, that would be the boundary. It's a closed set. It has the boundary points of that interval. Right? That's all I need. What else do we need? So, for instance, the set of all x, y coordinates, subset of R2, such that absolute value of x is less or equal to 1, and absolute value of y is less or equal to 1. What kind of set is that? A box? Yeah, like a square, right? Square. Does it include the boundaries? Yeah, that would be a closed set. How about the set all x and y, subset of R2, such that x squared plus y squared is less or equal to, no, just less than 9.
Circle radius 3
What is that?
Circle radius 3
Exactly, yeah. That would be a circle of radius 3, but only the interior, not the boundary included. Okay, so it is an open set. Now, do sets have to be open or closed? Is it possible to have a mix of both? Can you give me an example of a set that is neither open nor closed? Huh? Uh-huh. simple example would be if I made this one here, on one side I include the input, the other side not. That would be either open or closed, right? In that case here, if I change it like that, then it's neither open nor closed. Right, so that's just to tell you that the set doesn't have to be one or the other. But whenever we have certain requirements, we will say, given the function is continuous on an open set R, okay, or given the function is differentiable on a closed interval, something like that. Those are the requirements that we frequently refer to, so we only distinguish between open and closed in that case. So we need one or the other. Okay, let's see. Let's say we have f of x and y is equal to x squared minus y squared divided by x plus 1. Is that going to be defined everywhere? No, it's not going to be defined everywhere. Okay. So not defined. I heard 0, 0. Where else? Okay, exactly. Yeah. Not defined for all x and y such that x is equal to negative 1. But everywhere else it's defined. So the question is, what would be the limit as x and y approach point with coordinates, let's say 5 and negative 5. So obviously we can't plug it in, right? Because at that point it wasn't defined. Okay, but does the limit still exist?
We use L'Hopital's rule.
Yeah, so we don't have to go there yet. Plus we don't have L'Hopital's rule in that case. So what I can do is, though, I can look at limit x, y converges to 5, negative 5. And if I simplify that function, I have here x squared minus y squared. That's the difference of two squares. So that simplifies to x plus y times x minus y divided by x plus y. And if I exclude all those points x equal to negative y, then I can just simplify it to x minus y. X minus y, and that would be equal to 10. Okay, so the limit exists in that case, and that is equal to 10. So just because we cannot plug in our endpoint, or the one where our x's and y's converge to, it doesn't mean that the limit doesn't exist. You've seen that in calculus 1 probably, when you had a function that was defined like f of x equal to x squared minus 4 divided by x minus 2. And you have here 2, and then there was a function that looked like that, and it had an open circle here, right? Because at that point itself it was not defined. But the limit as you approached x from the left, or if you approached x from the right, the limit did exist. And that limit was up here at 4, I believe. Do you remember that?
Yeah.
It's safe to say yes. All right. So what else we got? Well, then we can look at the definition of continuity. so what was the definition in calculus 1 for continuous function? Exactly, yeah. So if at x equal to a, the function value exists, f of a exists, and if the limit of f of x as x converges a exists, and those two are the same, then the function is continuous. Okay? So that is, for instance, if I had a function that I defined like this, that function is not continuous, right? Even though here at a it is defined, it's defined to be that value up here, right? And the limit exists too, but the limit and the function value are different, right? So that function wouldn't be continuous, but at least not in x equal to a. But everywhere else it would be continuous. And in other words, the function was continuous if you could draw it without picking up your pen. So now our definition for functions that are defined in R2 is going to be very similar. Definition, continuity. F is continuous in point AB if the first one is that f has to be defined at that point. F is defined at AB. Second, the limit of x and y approaching AB, f of x and y is equal to L. That means limit exists. And the third one is that L is equal to f of a and b. If those three requirements are satisfied, then the function is continuous. So you already saw a function that was not continuous, right? The one where we had approaching it along the x-axis, the limit was equal to 1. Approaching it from the diagonal, the limit was equal to 0. Or the other way around. Well, there the limit didn't even exist, so therefore the function cannot be continuous. Let's look at so, I mean, for polynomials, you already know that they are going to be continuous. But how about the limit as x and y goes to 1, -1? One -2, I mean. And our function is y squared plus 2xy divided by y plus 2x. So that one will be continuous in that point. Yeah. So that is equal to, yeah, the limit is going to exist if we let x and y go to 1 and negative 2. The function itself exists at 1 and negative 2 as well. And because the limit and the function value are going to be the same, we can just say it is equal to, you plug in the values, you get 1 plus 2 times 1 times negative 2 divided by negative 2 plus 2 times 1. Oops, were we right about that?
Y squared is 4 not y.
Can we simplify and take the y out? So the y plus 2 cancels out. We look at y.
Negative 2 is squared.
Yeah.
What about the denominator?
Well, if you factor out a negative 2 from the top, you can do some cross canceling.
Okay, so but before we get there, we wanted to check if it is continuous, right? So for that, it had to exist at that point 1, negative 2. Now, if I plug in those values, negative 2 for y and 1, I'll get what is that equal to? That's going to be 0 over 0, right? So that would be 0 over 0, and that is undefined. Okay, but that's not going to be my limit. I'm just saying that f of 1 and negative 2 is undefined. So that means the function cannot be continuous at that particular point. F of x and y is not continuous. Could we define it at 0, 0 so that it becomes continuous? Yeah? So let's see. We have y squared plus 2xy divided by y plus 2x is equal to, if we factor out the y, you said, we have y times y plus 2x divided by y plus 2x. That is equal to just going to be y, correct? So now if I define that function to be define f of x and y equal to y squared plus 2xy divided by y plus 2x. We will define it as y. We will define it as y if y plus 2x is equal to 0, and we leave the definition as it is if y plus 2x is not equal to 0. So now if we extend it that way, then we'll have a function that is continuous everywhere. We'll define f, let's call it f tilde. Tilde of x and y is continuous everywhere. So how can we recognize continuous functions? What types of functions do you think are going to be continuous? What did you say? Planes, right? Polynomials, trigonometric functions, any addition and subtraction of continuous functions, any product of continuous functions is going to be continuous. Any composition of continuous functions, but here we have to be careful. We have a function that is defined on 2 dimensions going into R, or a subset of R, and we can only compose it with a function that is defined on only a subset of R. Okay. So if you have, in that sense, if composition of continuous functions, then composition itself is going to be continuous again. where the trigonometric function, like the tangent itself, is undefined. So let's just summarize it, how to determine continuous functions. Products, sums, differences, and quotients. Denominator unequal to 0 of continuous functions. Are continuous. What about compositions of functions? If f of x and y equal to u is continuous on just a set R, and g of u is continuous on the range of f, then g composed with f of x and y is continuous on all of R. So if we take our composition of continuous functions, then that's going to be continuous again. So you notice here we don't have a composition of two functions defined on x, y, right? Because the output for the functions that we consider are just subsets of R. Question. We have limit as x and y converge to a and b of x divided by x minus y. That limit, it exists under what conditions? Provided a and b are equal. A and b are equal. So x and y, they approach that point AB from any direction. Of course, we cannot evaluate the function when x is equal to y, but the condition is that a is not equal to b. If a is not equal to b, oops, forgot to say exists. If a is not equal to b, what else do we have here? If f is not continuous at a, b, then necessarily f of a and b is not defined. Is that true? If f is not continuous at a, b, does that imply that f is not defined at a, b? Yeah. Think back of that example that I gave you up there. The same can happen in R2 when you have a function that defines the surface. You can cut a hole in it and set at that hole you can set the function value higher. Okay, so the function is defined, but it's not going to be continuous at that point. Right? So that is not the requirement. F of x and y does not exist. So if f is not continuous, does it mean that the limit of x and y, f of x and y, as x, y goes to a, b does not exist? Is that true? Let me write this down. F of x and y is not continuous at a, b. That's the statement. Does that imply now that f of a and b does not exist? That is false. Like we just said that. Does that imply that limit x, y converges to a, b, f of x and y does not exist?
No, at all.
It's also false, right? Why is that not false?
Look back at our example.
So going back to that example, and was just a function defined on a one-dimensional space. The limit that exists, but it's still not continuous. Because if you went towards a, then the limit that exists from any direction. Again, the same example, if you have a surface, where you cut out a little hole and send it higher, as you're approaching in your x, y coordinate system that point where the hole is, the limit is still going to exist. It's going to be exactly in that circle, that limit, that function value. But the function is still discontinuous. Okay, so what about what was it? Either of the above. So if both of them are satisfied, then that would be true. So if the function is not defined at that point, and if the limit doesn't exist, then it's going to be discontinuous. Questions? Next one. Suppose that the limit as x and y converge to the origin of f of x has the same value on all paths of the form x, y is equal to mx, where m is a constant. Then it follows that the limit exists, it follows that f of 0, 0 is defined, or it follows that f of x, limit x, and y go to the origin exists. So let me write this down. And I already answered that question earlier. So we have, suppose the limit as x and y approaches 0, 0, f of x and y. This is the definition that m times x is equal to y, so it approaches on some straight line the origin. Is equal to L, so that limit exists. So what does that imply now? So answer A is, it does not follow that limit x, y going to 0, 0, f of x, y exists. That was answer A. Answer B is that it follows that. What's the question? That f of 0, 0 is defined, and C follows that limit x, y going to 0, 0, f of x and y exists. What's the correct answer?
Yes.
C. You cannot see? C? So we have here our origin, right? Is it enough that the limit exists, that it goes in on straight lines? It has to exist and be the same no matter on what path I'm approaching 0, 0. It has to be also the same if I'm going in on that spiral. So that has to be the same too. Just by having that the limit approaching 0, 0 on those diagonals exists and is the same, it does not imply that the limit exists at all. So the correct answer would be A. It doesn't follow that that limit exists. Because remember our definition was that x and y has to approach x 0 and y 0. We did not make any statement that it has to approach it on only certain ways. Any way you approach. You see the difference?
Can you go over it again?
Because in here we require that the x's and y's they approach the origin on those diagonal lines. Yeah, any slope, even on a horizontal line. That's not enough. Just because that limit for that type of approach is equal to L exists, that does not mean that the limit approaching 0, 0 exists overall, because there might be different ways to going to that origin for which the limit may not exist, okay, or for which the limit may be different. Okay. So the definition was independent of how we approach that origin. The limit has to be the same, no matter how we approach it. Yes?
So, how do I know that it does exist? So I take a diagonal and I go from the horizontal, and if they're both equal to each other, do I know it's continuous? Or whatever? How do I know that, oh, then everything else is continuous?
No. Just because it is the same by picking, let's say, two paths. You know, in the example I gave you earlier, I could have approached once from the left and once from the right, and could have seen, oh, it's the same. That is not sufficient to say that the limit exists, because there might be a different way of approaching it, for which the limit then is different. Yes?
So how do we test all cases?
There's no way to test all cases. For that we go back to our definition, saying polynomials are continuous, exponential functions are continuous. You know, we go back to any combination of continuous functions, and then we can say, well, that is continuous. So and those are going to be like really weird cases, you know, where you have something that where you go in on the diagonals and the limit is always going to be the same, and then you go on some other path, like for instance the spiral, and the limit is not going to be the same as on the other path. I mean, that is one of those extreme cases, and not like the function that we usually use. Questions? x and y is equal to y to the power of 4 minus 3x to the power of 8. It is continuous where? Where is everyone continuous?
Everywhere.
Everywhere, right? I mean, it's a polynomial. So all polynomials are going to be continuous. F is continuous. Where is it going to be continuous? Oh, really? You said everywhere. On R2. Okay. Write it like that. What about g of x, y, and z? Now I'm defining my function on 3 variables. So that's going to be a surface in R4. So that, of course, we cannot graph anymore. But if I define that as e to the power of x times y divided by z squared, that's going to be continuous where? Everywhere except where z is equal to 0. For all x, y, and z in R3 except where z is equal to 0. Okay. Now what about this one here? What would be the limit as x, y, z approaches 0, 1, 2? What would be the limit as x, y, and z approaches 0, 1, 2 of cosine of pi z e to the power of x times y? First of all, is that a continuous function?
Yes.
Yeah. Again, you have like a combination of continuous functions here. You don't have any denominators that become 0, no radicals of those negative radicals. So we can just go ahead and plug in number 0, 1, and 2. Well, 0 and 1, that makes my exponent 0. So you have cosine of 2 pi times e to the power of 0, which is equal to 1. So easy to evaluate. And last example that I have here. So again, we have a statement here. If the limit x and y approach a, b, f of x is equal to L, so that exists. Then the first statement is that f is continuous. Continuous at a, b. The limit equals f of a and b. And statement C is limit x goes to a, f of x and b is equal to L. Which one of those is true? Or maybe none of them. I don't know. Maybe that's an A. Goes towards A. example again, right? Here the limit exists, even though that's just like one dimensions, right? But the limit exists from the left and the right, but that is not the same as the function value, right? So then the function cannot be continuous. Okay, so A is clearly wrong. What about B? The limit equals f of A and B. Is that one true? No, it's not true either, right? The function doesn't have to be continuous. If that limit exists, it doesn't have to be the same as the function value defined at A, comma B. Think of that now in 2 dimensions. What about C? Is that limit also going to be equal to L? Huh? Yes. Yeah. So here we are approaching, before we said we have here our pointers, coordinates A and B, and we have to approach it from anywhere and, you know, in any shape. We need to approach it. And that limit for our function was equal to L. Now then, that includes also the fact that if I stay on B, which is that level, right, and I just approach it from either the left or just approach it from the right, that is just one of the many ways I was supposed to be able to approach it anyway. Well, then the limit still has to be the same. Yeah?
Maybe we'll have no problem with notation. When you wrote the limit f of x as xy approaches a b equals L on that problem there, that notation you're saying implied that from all directions that limit exists, correct?
Exactly. And
So on the problem over there, you wrote the same exact notation, but that notation did not imply that the limit existed from all directions.
Here the quantifier was not just that x and y equal to 0, maybe I wrote it too far off. I also said that y is equal to m times x.
Okay.
So here I restricted it to where I'm going towards 0, 0 and only on the diagonals.
Okay.
So you can think of that as one statement. X, y goes to 0, but x and y have a certain relationship. Any questions? How about g of x is equal to ln of x minus y? Where is that function continuous? Where is g of x and y equal to ln x minus y continuous?
Everywhere that x doesn't equal y.
Where x is not equal to 1? Okay, so we need to have here an argument that is positive, right? So where x minus y is greater than 0, that means x has to be greater than y. X greater than y, what plane would that be? Or what half plane?
It's going to be x.
There would be x equal to y, correct?
Yeah.
Now x greater than y, like this point over here would satisfy it, right?
Yeah.
So therefore, I can shade that whole lower part of that region. Okay. So that would be the solution set if you wanted to graph it. What would be the limit as x, y, and z approach 0, 1, 0? Limit x, y, and z approach 0, 1, 0 of e to the x z ln of 1 plus y. fold it